Okay, so we're back after a small hiatus over the Yuletide, and gonna learn how to functionally solve problems. Interesting. In this chapter, as you can see, I'm at a new PDF as well, because for some reason the website is not up anymore. But there is a there are PDFs out there. In this chapter, we'll look into a couple of interesting problems and we'll think about how to solve them as elegantly as possible using functional programming techniques. This will give you the opportunity to flex your newly acquired Haskell muscles and practice your coding skills. Oh, we're actually gonna do practice, not only reading anymore. So we've written a hello world and now we're gonna practice. Yeah, all that theory and no practice until now. I was kind of getting ready for having no actual practices in the book. I gotta say, if we're actually just gonna do a lot of practice now, that's a terrible layout for the book. I thought it was just gonna be theory, but if it's theory and practice, you want to intertwine them. I don't think Yuletide is the English name for it. Here it is. And go, wait, where is it? Need this. Let's see. Open Yule. Wait, you spell it with J or Y? I don't remember. Yuletide. Yule. Yule, also called Yule, Juleblot, and a lot of others, is a festival historically observed by the Germanic peoples. Scholars have connected the original celebrations of Yule to the Wild Hunt, the god Odin, and the pagan Anglo-Saxon Mother's Night. Later departing from its pagan roots, Yule underwent a Christianized reformation, resulting in the term Christmastide. Some present-day Christmas customs and traditions such as Yule log, Yule goat, Yule boar, Yule singing, and others may have connections to the older pagan Yule traditions. Sorry, I went on a sidetrack there. Back. Colgatin on tab says, we just had Hello World. No practice? What are you talking about? Yeah, alright, we did do Hello World. Does that count? I don't know. Julo is Finnish. It's mentioned there. Yeah, exactly. It's Yuletide. So it works. It works just fine. Right, reverse Polish notation calculator. I have no idea what that is. What are we doing? Alright, so this is a problem that we need to solve, maybe. Right, usually when we work with algebraic expressions in school, we write them in an infix manner. For instance, we write 10 minus 4 plus 3 multiplied by 2. Sure. Addition plus multiplication, subtraction minus, what do we say that? Times, right? Multiplication, we say that times are infix operators, just like the infix functions in Haskell. I remember that. Plus, lm, and so on. As humans, we can parse this form easy in our minds. The downside is that we need to use a parenthesis to denote precedence. Wait, why is that a downside? I mean, don't get me wrong. I dislike Lisp as much as the next guy, but we're talking about maths here, not Lisp. Another way to write algebraic expressions is to use reverse Polish notation, or RPN. In RPN, the operator comes after the numbers rather than being sandwiched between them. Right, so we have prefix, infix, and suffix. Why not just call them that? So instead of writing 4 plus 3, we write 4, 3 plus. But how do we write expressions that contain several operators? For example, how would we write an expression that adds 4 and 3 and then multiplies that by 10? Why are we doing this? It's simple. 4, 3 plus 10 multiply. Because 4, 3 plus is equivalent to 7, that whole expression is the same as 7, 10 multiplied. Okay? Calculating RPN expressions. To get a feel for how to calculate RPN expressions, think of a stack of numbers. We go over the expression from the left to right. Okay. Every time a number is encountered, put it on top of the stack, push it onto the stack. When we encounter an operator, we take the two numbers that are on top of the stack, we pop them, use the operator with those two, and then push the resulting number back onto the stack. When we reach the end of the expression, we should be left with a single number that represents the result, assuming the expression was well formed. Can't we just do this with I was gonna say prefixes, and we could, but usually we go from left to right, right? Left, right, right, left. Oh, wait. 10, 4, 3, so that would be what, 17? And then multiplied by 2. I don't know what this is. Would make them negative, so what? 17 multiplied by 2 is what? 34? And negative 34. Right, we push 10 onto the stack, so the stack consists of 10. The next item is 4, so we push that onto the stack as well. The stack is now 10, 4. We do the same with 3, and the stack is now 10, 4, 3. We encounter an operator. We pop the two top numbers from the stack, so the stack is just 10. Add those numbers together and push that result to the stack. Stack is now 10, 7. We push 2 to the stack, so the stack becomes 10, 7, 2. Oh. Okay. Plus only takes 2. All right. My mistake. Plus just takes 2 variables. Shit, they're not called variables. Parameters. So that's the 2 parameters. So we have 10, 7. Then we have 2, so we have 10, 7, 2. And then we have multiply. That means 2 and 7 multiplied. 14. 10 minus 14 is minus 4. I think I lost track of something along the line, but I think I get it now, yeah. We push 2 to the stack, so we got 10, 7, 2. We encounter the operator, we pop 7 and 2 off the stack, multiply them and push the result to the stack. Multiplying 7 and 2 produces 14, so the stack is now 10, 14. Finally, there is a minus. We pop 10 and 14 from the stack, subtract 14 from 10 and push that back. The number on the stack is now minus 4 because there are no more numbers or operators in our expression. That's our result. Suppose I do see the value of doing it that way. Do it all the ways around. Oh, and here we got a visual representation of what was going on. 10, 10, 4. Right, we add them all to the stack. 10, 4, 7. Then we have 3 plus 4. Boom. 2 multiplied by 7. Boom. 10 minus 14. That's how to calculate RPN expression by hand. Now let's think about how to make a Haskell function to do the same thing. Oh, it's not implemented already. So we do have implementations of prefixes and infixes, but not suffixes. Right. Writing an RPN function. Our function will take a string that contains an RPN expression as its parameter. String like this, for example. This is the same as before. Yep. And give us back that expression's result. What would the type of that function be? We want it to take a string as a parameter and produce a number as its result. Yeah. Oh, a double. Of course. Just to... I was thinking a number or something, but a double makes sense, yeah. Well, Continuum tab says boobies. Lol. Wait. Did I miss boobies? Right, where were we? Let's say we want the result to be a floating point number of double precision because we want to include division as well. So its type will probably be something like this. Oh, right, it says boobies right there. I missed it. Boobies! I remember that from high school as well. Note, it really helps to first think what the type declaration of a function should be before dealing with the implementation. In Haskell, a function's type declaration tells you a whole lot about the function due to the very strong type system. I have not been doing that when I've been building functions. Maybe I should be doing that. Boobies! Right. When implementing a solution to a problem in Haskell, it can be helpful to consider how you did it by hand. For our RPN expression calculation, we treated every number or operator that was separated by a space as a single item. So it might help us if we start by breaking strings like this into a list of items like this by using the words function. Yeah, there's a words function to split it up like this. Continuum tab says or tissit in Finnish 715517. Tissit, what does that mean? That tits in English? Right, next up, what did we do with that list of items in our head? We went over it from left to right and kept a stack as we did that. We're gonna make a fold. We're making a fold. Does that process remind you of anything? In I Fold You So on page 73, you saw that pretty much any function where you traverse a list element by element and build up, accumulate some result, whether it is a number, a list, a stack, or something else, can be implemented with a fold. In this case, we're going to use a left fold because we go over the list from left to right. Accumulator value will be our stack, so the result from the fold will also be a stack. Though, as we've seen, it will contain only one item. Oh, right, yeah. One more thing to think about is how we will represent the stack. Let's use a list and keep the top of our stack at the head of the list. Adding to the head, beginning of a list, is much faster than adding to the end of it. So if we have a stack of, say, 10, 4, 3, we'll represent that as the list 3, 4, 10. Oh, that is rough. Now we have enough information to roughly sketch out our function. It's going to take a string like this and break it down to a list of items by using words. Next, we'll do a left fold over that list and end up with a stack that has a single item. In this example, a list of -4. And we take that single item out of the list, and that's our final result. That confused me a little bit. Something that I missed out from the folds. So the accumulator is going to be a list. That's our stack, right? So we're going to have this list, and then we're going to have a secondary list that is our accumulator. Maybe? Right, here's a sketch of the function. Solve RPN. We take a string and return a double. Okay. We will check this out. We will first make words out of the expression, turn it into a list, and then we will fold left over that function with our folding function and a list. Yeah, our accumulator is a list. Interesting. Right, and our folding function is gonna stack item ... Right. And stack item then, since we have our list over here, stack item is gonna take two items, right? Our stack is always two items. No. We're gonna add 10 to the list. Yeah, the front of the list. Then we're gonna add 4 to the front of the list. That's our stacking, right? Then we're gonna stack 3 to the front of our list. Then we're gonna stack plus. Here, that's where it becomes a weird function, right? Where it becomes intricate, isn't it? Just stacking these numbers on top is... It's kind of like we're just flipping the list, right? But the stack function, we're gonna have guards, right? Depending on what we're doing. So a guard is if we run into like a plus, a multiplier, a negative, or something like that. Then we're gonna take the... Yeah, we're gonna take the current head, the two heads. We're gonna take the head and second item, I don't know, and plus them together. Probably through like a head plus head. Yeah, like a recursive thing, kinda. Colgitunotype says pretty much, but we're reversing. Flip is for functions, right? We're reversing the list, not flipping it. Flipping it we do with functions, which is similar to what we're doing, I suppose. Alright, so that's how our stack item thing is gonna work. That's much better. The folding function will take a stack and an item and return a new stack. We'll use pattern matching. Right, yeah, we don't need a guard, we need pattern matching. To get the top items of a stack and to pattern match against operators like multiplier and minus. Here is Here it is with the folding function implemented. Alright, here we go, where our folding function, yeah, exactly, we take the head and the second and the rest of the list. So our folding function, right, yeah, we're returning this list. Folding function, if we get multiply, that's our folds, right? So if we run into a multiply, we will multiply x and y on top of the list. Yeah, on top of the tail. Yeah, so x and y is replaced by x multiplied by y at the top of the list. At the head of the list, I'm sorry. Well, it's on top because we were looking at the stack before. And the same thing for plus and minus. However, if it's not one of these, we will just... Right, we will folding function, we will take the list. Folding function, and it's a number string. Oh, right. Exactly, because... Yeah. Our original list, it's all filled of strings, right? So when we run into a number, which is all the other versions, right? Where is it? Yeah, like the 10, the 4, the 3. We just read them to make sure that they are now doubles. That is it, right? They're gonna be doubles. They're not... Are they gonna be num type class? No, they're gonna be doubles because of the lazy evaluation. So yeah, when we read the number string XS, they are all gonna be doubles. Yeah. Yeah, Haskell can figure out how to read it because of the type inference, exactly. Because we have this here. If we didn't write this out, there would be no inferring what type it would be. That is why it's a good thing to have this here. Because all of these would not turn it into a double. All of these would turn it into an int. Or integer, I suppose. We decided to do it double from the get-go. But if we had a function for division, it would probably then turn into... Yeah, it's a member of num. Down here, it's a member of num. But here we specify. But if we had the dividing function, right? Multiplication plus minus, if we had division as well, it would not be a member of num, right? It would be a member of... I don't remember the name of that. Were they called floats? No? What's the type class with float and double? There's a type class. I don't remember the name for it though. Volgatino tab says could be int, integer, word 8, float, double, or whatever. It's called floating, I think. It doesn't matter a lot, but yeah. It could be, right? If we cut this out, it would be a num. Right? If we cut this out from the function, this would be a num type class. Would read it as. But since we have it, it's gonna be a double. And if we had division, it would be a floating, we think. Don't take our word for it though. Right, we laid this out as 4 patterns. The pattern matching will be tried from the top to the bottom. Yep. First, the folding function. Actually, let's keep the function right here. Let's not remove it from the string. Volgatino tab looked it up and says, yeah, it is floating. And it's integral for the int and the integer. That's called an integral. Right. First, the folding will see if the current term is asterisk, a star, a multiplication. If it is, then it will take a list like 3, 4, 9, 3 and name first two elements, x and y respectively. Yeah. So in this case, x would be 3 and y would be 4. Exactly. The head and the second element. Index. Ys would be the tail, the rest of the list. It will return a list that's just like ys, but with x and y multiplied as its head. With this, we pop the two topmost numbers of the stack and multiply them, and push the result back to the stack. If the item is not multiplication, the pattern matching will fall through and plus will be checked and so on. If the item is none of the operators, we assume it's a string that represents a number. If it is a number, we just apply read to that string to get a number from it and return the previous stack, but with that number pushed to the top. Colgate InnoTab says, and to be a member of floating, they also have to be members of the fractional. Oh, look at that. Lots of type classes. Lots of type classes. Right. For the list of items 2, 3 plus, our function will start folding from the left, and the initial stack will be an empty list. That's our accumulator. It will call the folding function with an empty list as the stack, the accumulator, and add 2 to it. Add 2 as the item. Because that item is not an operator, it will be read and then added to the beginning of the list. So the new stack is now 2, or it is 2, or without the syntactic sugar, it's this, right? That's what it looks like. Then we get the 3, we will pop that on the top of the list. Alright, then it's called for the third time with 3, 2 as the stack and plus as the item. This causes these two numbers to be popped off the stack, added together and pushed back. Final stack is 5, which is the number that we return. Play around with our function. Right, the problem, this puts a lot of responsibility on the user, right? To build a proper what was it called again? RPM? Something like that. Now don't I heat some beans? No soup today, eh? You're gonna add chili to it? Oh, it says RPN right here. Yeah, RPN. That's what we expected. Do 3.5 plus, we get 5.5, that's what we expected. Wow, look at this one. Right, we were gonna flip them all, so that's gonna be 66 plus 55, right? EH. Let's follow along with that one. Right. Yeah, we're gonna do all of those, and no, yeah, we're sure. 55 plus 66, and the resulting answer is what? It's 100. You know, I'm too tired to do mental gymnastics maths, right? These multiplied by 33, and this gonna be this minus 12, right? Or is it 12 minus this? No, this is on top of the stack. So since that is the top of the stack, it's going to be minus 12. Shit, something broke though. No, I did something wrong. Because we have more numbers here. 121. We have 1, 2, 3, 4. So we have that. 1, 2, 3, 4. Right, I think I'm considering something wrong here. No, those are gonna be added together. We know that for a fact. And then they're gonna be multiplied with 33. And that is what's gonna happen. Minus 12 plus 34. So what we're gonna have... Actually, what do we return from the function? Yeah, you were right. Yeah. We return the head. So the 90 here is not going to be relevant at all. We're just going to do all that math, and then we're going to be left with... Yeah, the 90 is not relevant at all, is it? Yeah, that's why they're doing the same thing here, but they're... Yeah, they're adding a negative. Is not. And the two answers become completely different. I'm confused. Alright. It works, but that's because of that. I think my confusion comes from the RPN and not from the Haskell. We'll get in on tabs this ands and 90 minus ands. What is ANS? And this... Wait, isn't it this minus 90? Huh? The shorthand for answer? Well, that doesn't really help. Okay. Adding more operators. Did we add some more operators? Yeah. Do that. One nice thing about this solution is that it can be easily modified to support various other operators. They don't even need to be binary operators. For instance, we can make an operator log that just pops one number off the stack and pushes back its logarithm. We can also make operators that operate on several numbers, like sum, which pops off all the numbers and pushes back their sum. Let's modify our function to accept a few more operators. Right. And these, we just add them. Right. Pop that off. And yeah, exactly. Alright. The slash is division, of course, and star is exponent. Oh shit. Exponentation? Yeesh. Alright. By the power of 2? I don't know. With the logarithm operator, we just pattern match against a single element and the rest of the stack, because we need only one element to perform its natural logarithm. With the sum operator, we return a stack that has only one element, which is the sum of the stack so far. I think that making a function that can calculate arbitrary floating point RPN expressions and has the option to be easily extended in 10 lines is pretty awesome. It is pretty awesome, right? Note, this RPN calculation solutions is not really fault tolerant, yeah. When given an input that doesn't make sense, it might result in a runtime error, but don't worry, you'll learn how to make this function more robust in chapter 14. Alright, we didn't have to type anything out. It was more theoretical in nature. It was an exercise where they held our hand through the entire exercise. Right, and we'll get back to it another day. Because that's a good spot for lunch, isn't it? Right, so have a good one, yeah. You could had tried to solve it on your own, says Colgate on tap. Oh, no, not that one. Right. That's a confusing one. I could have, but let's not. Let's not. Alright, have a good one. Yeah, cheers.